this video we are going to talk about how we use the interrupts on the ATMEGA328P, and although it won't be a very in-depth video focusing on all the theoretical concepts, it is practically orientated to show you how to get the interrupts working and to use both the timer 1 interrupt. And although there's multiple different ways in which we can use the timers, we are just going to start with the basics. And the timer 1, I'm choosing timer 1 because it's a 16-bit timer, so you can get a large timing sort of byte in there. And then we'll also do external interrupts. So at this stage of the course, you know more or less what an interrupt is. Well, hopefully, because you did it in the previous subject. But just a brief reminder is that, remember, your CPU, so in your main program, for instance, if this is your main program, this is everything that will sort of be handled by the CPU. CPU just keeps running here. And then if you have an interrupt that is enabled, what happens is it allows you to, so the CPU never has to monitor any of the interrupt triggers that you are working with. CPU can just do what it wants. There's other circuitry that monitors the interrupt, and should an interrupt occur, what happens is it branches out, it services the interrupt, and when the interrupt is done, it just comes back to the exact place where it left off, and the CPU can continue sort of executing the code. So in the ATMEGA, we have quite a few interrupts, as you can see. So this is the interrupt vector table. Now the reason why this is important is because without proper vector addresses, we cannot execute interrupts. Why? Because remember, as you saw here in this crude drawing of mine, when the controller receives an interrupt and it has to branch to that interrupt, you need the vector address, and that vector address is important because that's basically where you are telling the controller to go and where it will find the subroutine that it should execute as part of the functionality of what you want it to do should that interrupt occur. So the vector address is always associated with interrupts, and we sort of have multiple vector addresses. And so you can see we have our two external interrupts. Then we'll focus on that, and we'll focus on a lot of what we're doing with the timer. So you can see there's a lot of timer associated interrupts. There's also interrupts for SPI, for serial communication, and then for the ADC. So there's really a lot happening in terms of interrupts. But what we are going to focus on today is we are going to look at the timer 2 overflow, and we are going to then also look at the interrupt 0 and interrupt 1. Those are the external interrupts, so triggered by something external to the microcontroller, whereas this is something that is timer driven and it is internal to the microcontroller. Okay, so the first thing I just want to bring your attention to is, in order for us to use any of the interrupts on the ATMEGA controller, is we have to speak to the status register and enable the global interrupts. So this I bit here is the global interrupt enable, and that's located within the status register. Now, in order to do that, we have to include this header file. Whenever we work with interrupts, its hash includes avr/interrupt.h, and then there are two macros built into that header file, and that is SEI and CLI. And so this is to set all interrupts and clear all interrupts. So it's basically we enable all the interrupts with the function SEI, and we clear all of them with the CLI function. and I'll show you exactly how that works in a moment. So remember the interrupt service routine here on the ATMEGA. You started with what the coding looks like is it always starts with ISR capital letters, and then you'll actually, in the brackets, you'll have the vector address associated with the interrupt you want to occur. And then in your curly brackets, that's where you'll have your actual code of what it needs to do should that interrupt occur. Now, these vector addresses correspond with the vector table that I showed you in the beginning. But here we refer to them sort of in names. We use a symbolic format to address them. We don't use addresses like 0x09 per se. I'll show you exactly how to know what is the correct name to use for the associated interrupts and where to find that inside that header file that we've included. So if we now just see if we can get to an example using timer 1. There's a few things we have to consider in order to get the timer to work. So there's a few registers we have to speak to. The TCC R1B register, that is your timer counter control register B. Now the important thing that we are concerned with here is basically we are going to focus on those 3 bits there. In this register, and the reason why that is important to us is that allows us to set the sort of the division factor, or to set the prescaler, and so that determines how fast your timer will sort of run, because it derives the pulse for the timer from your main crystal, which is on the board. And I'll show you how that calculation works, but you can see there's multiple options you can use here to basically set up that sort of the clock for the timer, if you will. Then there's TCNT1, and then you'll see it has an H and an L, and this is the register where you write the timing byte to. Now if you recall, on the 8051 microcontroller, the timing, once you've loaded the timing byte, it basically counts up from that value. So if you have your timing byte, because it's an up counter, it always counts up from the timing byte up until the maximum count for that register size. So if it's an 8-bit register, it's 256 or 255. If it is a 16-bit counter, then it's 65,300 and something. So but it always counts up from the timing byte, so it basically just counts the difference between whatever is your maximum capacity of that register and the actual timing byte you load. And this is, in this sort of the count there, is what you will derive your time delay from. So that's also how we work with it in this context. And then lastly, we are also interested in the TIMSK register, that is the timer counter 1 interrupt mask register, and here we are interested in this bit over here. And the reason why we are interested in that is because that is the timer 1 overflow interrupt enable. So here we enable the interrupt specifically associated for using the timer in this function. You can see there's multiple other functions in which we can use the timer, but we are going to work on an overflow basis. And what that means is whenever it reaches terminal count. So once we've set our timing byte, is where it will start. So this is where it starts counting. Then it's going to run. It's going to count up until it reaches the terminal count, which is basically your max value. And at this point, you will get an overflow, and then you will actually, at the overflow, it will branch and you will execute whatever code you have in the interrupt service routine. Right. So let's say we have what we have a very simple thing here. So you'll observe there's two things happening. There is this LED that is flashing, And you'll notice there's a count happening on these on this bar graph. So, and this is just the purpose that I'm trying to illustrate, is this part of what you're seeing is what is done in the main program by the CPU. This is handled separately. This does not reflect in your main program. This is what we handle with the interrupt service routine, and this is dealt with separately in the main program by the CPU. Now, our objective here is to do a 100 millisecond delay with an LED that flashes. So you'll probably think, but this flashing here is not 100 milliseconds. You are absolutely correct. Remember, on Proteus, the timing is quite off when it comes to simulation. So the calculation, though, is sound, and it will give you a 100 millisecond delay, but it simulates slower, which works well because it allows us to observe actually what is happening. So let's say now we know that we want a 100 millisecond delay. We sort of, that's our chosen time delay. Now you can decide on different values, and I think actually you'll see here in the code there's a bit of a discrepancy between the actual number written into the code versus what we will derive from the calculation. That's just because I've fiddled with it, but I'll show you the calculation for 100 milliseconds. So our crystal frequency on the board is 16 megahertz, so that's basically what we use. So we want to determine the timer tick frequency, and what is that? That is the frequency that is basically going to drive the timer. So if that's like just a pulse that is going to cause the timer to constantly sort of increment, it's the timer's heartbeat. Let's think about it like that. So in order to get that frequency, we take the oscillator frequency and we divide it by sort of like the prescaler or divisor factor that we have. Now if we go back to this table, you can see there's multiple. We can work with divided by 1, divided by 8, divided by 64, all the way down to 1024. So I'm going to divide it. I'm going to use the 1024 one for my division. And let me just get back there. So, and that's going to give us the frequency. So we basically take our, so we start by getting the frequency. Okay, so we know that we've got 16 megahertz. So we've got 16 megahertz, and we divide that by 1024. And if we do that math, it is going to give us 15,625 hertz, so it's 15.625 kilohertz. So this is the frequency that the counter will see as its heartbeat. So now what we want to do is we want to get the period of that, and we know that period is frequency inverted, and that is going to now give us 64 microseconds. Okay, so we've got 64 microseconds is the period basically. Now we can go and we can say, okay, so in order for us to to now have a 100 millisecond delay, we want to know how many pulses is it going to take for us to get to 100 milliseconds, and that's what we basically do in this portion over here. We say, okay, if I've got 100 milliseconds, which is what I want, and I divide that by 64 microseconds, then we end up with a value of 1562. Now this is basically the count that I need. So it needs to count 1562 times for me to get a delay of 100 milliseconds. But if you recall, this is an up counter, so this is the difference that it needs to count. So I need to say, okay, what is the maximum count on a 16-bit register? And that is what we have here. It's 65,535. This is the maximum count you can get out of a 16-bit register. You subtract from that your 1562, which is what we have here, and that gives you an answer of 63,937. Now this is your timing byte, and that is what you load into the appropriate register, because it's from this point that it will basically count onwards. From this point it will count on, just to keeps incrementing, basically counting 1,562, hits 65,535, and then you get the overflow. So there's our calculation. Now let's see what should we do in our code. So firstly, remember, we always want to include the header file. We want to make sure I have my global interrupts enabled. We want to enable the configure the prescaler or divider. We want to load the count value. We want to make sure timer 1 is enabled, and then we need to make sure there's a service routine written, and then there's also a main program for us to that the CPU will basically be busy with. So let's take a look at the code for that. So here you can see we've got our basics. The only new addition is the avr/interrupt.h header, so we have that. So what I've done, I just have my LED that I've defined and given the name, and that's associated with port beacon 0, so I will refer to it as LED. Now I'm firstly going to just look at we'll come back to the interrupt service routine just now. We are going to start with just looking at the main. So here you can see I've got my 16-bit unsigned integer, and I just defined a value as count. Now you'll see in my program here I'm not using this variable at this moment. I was planning to use that at a later stage, but I just defined it in case. Then I set up the direction of my LED, so my LED is set up as an output. Then I set up the direction of port D. Port D is also set up, the whole of port D is set up as an output. Here you can see, here I only set port B, the pin associated with the LED, as an output. Then I enable my global interrupts, so SCI, so this enables my global interrupts. Then I now do three things. Firstly, we set the prescaler to 1024, so that gives you a value of 05 that you are writing into this specific register. And if you want to know why it's 05, if we refer back to this register, then you'll see 101 is because I'm writing this value, which is 1024 for the prescaler. That's why that value is 5. Then TCNT1, this is your timing byte. Now you'll see here I've got 57,722. That was because I fiddled. Ideally what you would expect to put in there is this value for 100 milliseconds delay. I played around with it a bit, and this will actually give you a 500 millisecond delay. And then lastly, you just want to make sure the timer 1 overflow is enabled, and that is in the TIMSK1 register, and I just enable that specific interrupt flag. Then so that will make, at this point the interrupt is ready to go, and it's going to take care of itself. So now we go into the main part, and this is what the CPU will occupy itself with. And here you can see I just have a for loop, and count D, port B will just basically display the count with 200 millisecond. At 200 millisecond intervals, port D will display the count. But now remember, when it simulates, it looks a bit off, but that's because Proteus simulates timing. Timing in Proteus isn't necessarily all that well set up, so you sort of just have to use your imagination. But from a technical point of view, we know we are correct. So let's look at the interrupt service routine. So here you can see it's ISR. Always we start like that, and here we've got timer 1 underscore OVF underscore vec. So this is timer 1 overflow vector. So this is the vector address for timer 1 overflow, which is the mode or the interrupt in which we are, the way that we are using is we are using the timer 1 overflow vector interrupt. That's a specific interrupt. If you recall from the vector address table we saw in the beginning, that is specifically an interrupt associated or with timer 1 that we can use. And all that we do is we will toggle the LED on port B. So I've just, this is simply to toggle this toggle. So if it's on, it turns off. If it's off, it turns on. So this will toggle the LED on port B. And then you just have to reload the timing byte value again. And you remember this is what you also had to do on the 8051, especially if it wasn't working in auto reload mode. In this case, it's not auto reload. You have to automatically reload itself. So what you do is because the only reason you would come here is because you've expired. The timer has expired. And then what you do is you have to, after you've executed, you reload the counter, and then it will basically run again. So the CPU will do this part, and whenever there's an interrupt, it will quickly come and execute this, and then it will go back. So I promised I will show you where do we get this name? How do you know that this name is that? Why is it that? And so you can see here, if you go into Atmel Studio and you navigate to this portion, what you do is basically, in order to get that that menu, so you'll see there's a dependencies, and once you drop down on dependencies, there's this IOM328P.h. If you open that, you can scroll down, and that's the whole header file for all of the names you can use. And you can see here then is where you get the name specifically that you can use for timer 1 overflow vector. Okay, so this is how you know what to call this. If you wanted to use the timer 2 overflow vector, that's what you would call it. If you want to use timer 2 compare vector, this is the name you would use. And so these are just some of the different names that you could call it. But so you can see we've selected this one, timer 1 overflow vector, and that is the one that is how you know the name. So in order to get access to this, all you have to do is before you start writing your program, you just compile it once. So once you've done this part, you basically type it, and you still have an empty main, but you've made sure that you've included this, and then you just say build the project. And once it's built, then you'll see when you click here on dependencies, it will now include under dependencies is where you will find all of these associated files that you can see. And then if you click on dependencies and it drops down, then you get all of these included things, and then you can see this is the one that you want to know for the interrupts. But it also has the interrupts, it has all your IOs as it's defined, it has everything, and so that's why it's useful. So that's it for this video, and this will help you to get your timer interrupts sort of going, or at least timer 2. And then in the next video we will talk about using external interrupts specifically, or the only two we have in this case is interrupt 0 and interrupt 1.